when I was like 17, 16 years old, I was already telling my classmates, I want to find a cure for aging. So it's basically an obsession, a lifelong obsession. So skin is a very good model for aging because you can see it. It's a very complex organ. It's made of many, many different cell types. It's connected with, of course, the blood system, the nerve system. It has its own muscle system for the hair. If you manage to solve skin aging, first of all, you're going to be very rich because a lot of people care. And also you will probably have a lot of hint of how to apply the same thing to other organs. For someone who is obsessed with aging, it's very easy to obsess on skin aging because that's what you see, right? You look at yourself in the mirror and you're like, oh my God, I have to do something. Biology is never all or nothing. It's always a continuous.
There are studies that claim that human brain, so neurons, can potentially function only up to 120 years because they cannot divide and accumulate damage. So where is truth here?
Mm-hmm. And that's a good question. These numbers of 120, they don't come from understanding of molecular aging. They come from study of human population. All of these papers, I checked them. The oldest person ever to live was 122 or something like that, and never got, beaten since. I still believe that if you fix problems where they are all over the place, you should be able to live. I mean, I don't see why there would be a biological limit.
Do you believe that naming aging a disease would solve something?
People who are asking for it, they're asking for it for a good reason. It's because once you declare it a disease, then you can have fundings for that. You will have clinical trials that would be more defined. It's a technical reason, basically. The part that would probably suffer from it is the rest. So, for example, supplement industry relies on the fact that it's not a disease. Because the moment you say it's a disease, you cannot have a pill that say it acts on aging because then it's a drug. So you cannot. And even the cosmetic industry is also in that situation. Anti-age, you will see that everywhere on every cream in the world would be a forbidden term because it would be the same thing as saying anti-cancer.
Wow, this is a very, very interesting perspective. I've never thought about it, but this is really, really smart. Oh, François.
Hello.
Comment ça va? Thank you for coming. I would like to start by asking you to briefly introduce yourself for our audience so they know who you are and what you are busy with.
Okay. So I'm François-Xavier Pellay. That's my full name. I'm a scientist. I'm a biologist by training. I have a background in biochemistry, in organic chemistry as well. My PhD was in bioinformatics. So I went into many different areas of biology, I would say. I also learned about microbiology, about evolution, about genetics. So during my career, I basically went in very broad, let's say, different aspects of biology. And the reason for that is that my general interest is aging and longevity, and was since the very beginning of my career. So I believe that aging is a very complex topic. So the more you know about biology, the more you can understand it. So you can look at it at different scale, through different aspects. And so that's why my background kind of reflects my interest for aging.
So how did it happen? How you got interested in longevity?
Oh, yeah, that's an interesting story. It started really early, I would say, for this kind of interest, because when I was already a teenager, when I was like 17, 16 years old, I was in high school, I was already wondering, what I want to do. And what I want to do is find a way not to get old and not to die. So I was already telling my classmates, I want to find a cure for aging. So it comes from a long, long time. It's basically an obsession, a lifelong obsession. So yeah, somehow it made my life easy because I could just direct all of my effort towards that goal during my whole life. So that's that's unusual, I would say, early for longevity.
And that's really helpful, I think. And probably it looked a bit odd for your classmates. Yeah.
Of course. Well, they're much more interested now. They're glad that I went into that direction. But yeah, originally it was a little bit strange that someone so young would be interested in aging. You know, there's no real reason I can find. Maybe because I'm not religious and you know, I needed to find a solution that is not heaven for what happened after that. So basically, there's no solution for me. So only trying to postpone as long as possible and you know, having an enjoyable life is a good reason also to try and make it as long and healthy as possible.
Absolutely. And I know that in the last years, you've been focused on skin rejuvenation as a part of longevity. Why this thing?
Yeah, so I mean, that's not my only interest, but that's a big part of it. There's several reasons for that. I would say one of the main reasons is because I ended up working with the cosmetic industry for over 10 years. So I became an expert in skin by side effect. I had a lot of freedom. I could do basically any research I wanted. My research was not only focused on skin, but I did learn a lot about it. That's one reason. Another reason is that skin is a very good model for aging because you can see it. And I feel like weirdly enough, it's a little bit understudied because you have cosmetic industry, which is huge, but they mostly try to find a way for you to look younger, but they don't really have solution to make the skin biologically younger, right? There's very few options for that. And people think it's secondary, it's just the look, it's not that important, but actually it's much more than that. And it's a very reachable organ. So if you want to make some improvement, you can just inject directly into the skin. It's much easier than the brain, for instance. So as such, it's an interesting organ. Plus, it's a very complex organ. It's made of many, many different cell types. It has different layers, has different function. It's connected with, of course, the blood system, the nerve system. It has its own muscle system for the hair. I mean, it's a complex organ, right? So you can look at it in many different aspects, and you can, you know, if you manage to solve skin aging, first of all, you're going to be very rich because a lot of people care. And also you will probably have a lot of hint of how to apply the same thing to other organs, and some of which are much simpler. Like if you take the liver, for instance, it is a more simple organ than skin. It's constituted of less cell type. It has more defined function, and it's also have, I mean, liver is a little bit special, but like some organs are also suffering mostly from, let's say, intrinsic aging. So the, let's say, natural aging that goes with time, but skin is also suffering for extrinsic aging. So aging due to mostly sun exposure, but also pollutant and all things like that. And we are, as organism, of course, our aging depends on our genes, our molecular background and everything, but also the environment. So that's also why, in that sense, skin is a good model for aging.
I think that in general, skin is the biggest organ that we have. And I think it's very much underestimated and doesn't have enough attention because it's just all the time there, and we just perceive it as something normal. You know, if you think about a heart, it's somewhere inside the body. But here I can put cream on it. It looks older. I get wrinkles or whatever. So it's very, very visible. And at the same time, for just regular people, it looks like something simple, although it's not at all.
No, it's not. No. And it's actually, for someone who is obsessed with aging, it's very easy to obsess on skin aging because that's what you see, right? You look at yourself in the mirror and you're like, oh my God, I have to do something.
Yeah, I mean, like, look at that.
That's a good, I don't know how good is my heart because I cannot see it. It's beating. That's what I know. But, for my skin, I really can tell how bad it is. So yeah, that keep my motivation high.
So now we come to the big question. Many scientists, they claim that their goal is to reverse or cancel aging, but we need to start with another thing. What is actually aging? And I love to ask scientists this question because they never have an answer.
Well, I mean, there is answers. The problem is not that we don't have answers. The problem is we have too many answers. But
okay, go on.
But you have a variety of answers for this question. But I would say scientists now more and more agree on what it is. Aging, and you can take it in a very simple, the simplest possible explanation of aging is basically going from a new fully functional system that basically degrade with time. So that would be.
So it's entropy.
It is kind of entropy. Yes, it is entropy. Yeah, we can put it like that. But the interesting part is that it applies at every level of organizations. You can say it for a whole organism, but also for an organ. Organ can age, like skin, for example, we just mentioned. The cells themselves can age. So which means within a population of cells, within my skin, I have a bunch of cells, and those cells are not all the same age. So how do I know that some are younger or older? Just because by looking at them, some are way more functional than others, and they have no markers of aging, some do. And so you can also go down, you can look at the mitochondria. It's the same thing. Within your pool of mitochondria in each cells, you have some that are fully functional, so young in every aspect of the word, and some are old, some are dysfunctional, and they have to get degraded. And same thing at the molecular level. Like a molecule, even the simplest molecule, can either be normal, so as it should be, or it start to get oxidized, for example. Like a protein can be misfolded as well, oxidized. There's different kind of damage that can occur to it, and then that protein can be labeled as old, as aged, right? So I like to look at it like that. So that allow you to look at the whole complexity as it is, yet under the scope of a relatively simple functional versus non-functional.
Yeah, but what causes it? I mean, like we have biomarkers of aging.
So that's a different question. So defining it, that's one thing. And then trying to find out why it gets, why aging occurs. And that's also like basically the same thing as what I just said. If you look at it under the scope of its entire complexity, it's very hard to believe that there's a single cause. I mean, it's actually impossible that there's a single cause, because if you look at biology in its entirety, biology is extremely complex, right? It's made of millions of components interacting with each other and who have influence with each other. And basically, aging and biology is kind of the same thing, because you could look at aging at every aspect of biology. Could be looked under the aging aspect. So you could see any aspect of biological process that can be fully functional or not, and that can age. Basically, anything that doesn't work potentially have an influence on the rest, right? So that's like this network view, I can call that network theory of aging, that forces you not to think there's a single problem. So anything that is claimed, well, not all things, but many things that are claimed to be cause of aging are cause of aging, but none of them are the only cause of aging. So you can't say it's only due to mitochondria, or it's only due to DNA methylation, or it's only due to protein oxidation, or, it's all of that. And it's all of that because all of them are connected with each other. So some are like more fundamental. So that's why they created these hallmarks of aging with the intent of really finding the one that are the most causal. And some are just side effect of the rest. So if you have an overproduction of ROS free radical in the system, yes, a lot of things would get oxidized as well. And some of those things that are oxidized are, I would say, secondary. They just are less functional when they're oxidized, but some become also more important because if they don't work because they're oxidized, then they will create much more damage.
Why don't we age evenly? So why different types of cells in our body and why our organs don't age evenly? Because it makes no sense. I mean, like why my mitochondria are older than, I don't know, like cells in my lungs.
Well, I mean, biology function like that. Biology is never all or nothing. It's always a continuous. And within a population, like I was saying, if you take a population of mitochondria, there's in theory all identical, but so sometimes it's due to random accidents. It's just that some happen to have, for example, a mutation that occurs, accidentally, that will make them more prone to produce free radical. And of course, since they are the one producing it, they are the first target of their own production of free radical. And that's going to lead to that mitochondria aging faster than its neighbor. So that could be a possibility. So chance could be an explanation why aging is not homogeneous. Another thing is that your cell types, like you were mentioning, why your brain cells and your liver cells won't age the same way, for example, is because those cells are very, very different. And there are two types of cells that already you can tell how different they are when it comes to aging. You have dividing cells and non-dividing cells. And so, for example, skin cells divide a lot and they will have aging problems that are different than the cells that don't divide. So when a cell divides a lot, the risk is mutation, because at each division, you have the DNA that replicates. So you have a chance of mistakes being made, right? So that's what mutation is. It's just a mistake in the copy of the DNA, right? So those cells are more sensitive to DNA mutation. But other cells, like for example, neurons don't divide because, once they're differentiated, they're all elongated and stuff. They cannot divide. So they have other problems. They don't have mutation. It's not possible since they don't divide. but they have accumulation of problem, because a skin cell will dilute its problem at every division. So if it has like a lot of protein oxidized, at each division it will be diluted, and the production of protein will kind of rejuvenate proteins all the time. In a neuron, it's a much bigger problem. That's why when you look at neurodegeneration, for example, a lot of neurodegeneration disease like Parkinson, Alzheimer's, ALS, they all have something in common. They all have oxidized protein as one of the main cause. And the reason is because they don't divide. So they only can accumulate problems. So you understand that would already be one way to see the difference. But there's many aspects in biology that makes, and then you have genetic differences. Like you can also ask the same question, why would you and someone else, me, for example, would age differently? Like what is your, let's say, genetic weakness and what is mine? So maybe, I have a strong heart, but I have a weak immune system or whatever, it could be. And that can be in big part genetic as well. So the difference from people to people is their genetic variation. Plus, there's always this notion of chance, accidents that happens. Yeah.
Probably environment and the lifestyle.
And then environment,
so
of course.
things.
Yes.
We touched brain a little bit in neurons, and there is an ongoing discussion sparked by longevity enthusiasts like Aubrey de Grey, who say that there is no biological limit on how long people can live. And on the other side, there are studies that claim that human brain, so neurons, can potentially function only up to 120 years because they cannot divide and accumulate the damage. So where is truth here?
Mm-hmm. And that's a good question. I mean, as your limit came from the telomere reduction.
Mm-hmm.
Of course,
yeah, because they get shorter.
Exactly, at each division. So that's how they calculated, it must be 120 years, which happens to be the age of the oldest human. So that was a good prediction, except it wasn't a prediction. But the problem is that doesn't apply to neurons because they don't divide. So neurons don't have telomere that shorten, right? So it's only cells that divide, like fibroblasts, for example, who will have this telomere issue. They have genetic problem, basically. So, I mean, yeah, DNA problem. So it doesn't apply. It doesn't apply for neurons. Neurons have other problem, like we just said, of accumulation of problem. But overall, these numbers of 120, they don't come from understanding of molecular aging. They come from study of human population. All of these papers, I check them, because they are from time to time publication with these claims, and it bothers me. So I check on it, and each time it makes sense, but it makes sense only in the context that it's based on the current and previous human population. So of course, if you look at, it's like you're in the 19th century and you look at all the data available in the 19th century and your conclusion is it's impossible to cure bacterial infection simply because it was never done before. So according to all data, it's impossible to cure bacterial infection. But of course, it's not impossible. It just haven't been done yet. And so that's basically, for me, the bias of those studies is that based on current data, all the current population, none of them has been benefiting from proper rejuvenation method because there's none available. And of course, the population limit is the normal biological limit of humans is probably around 120 years because the oldest person ever to live was 122 or something like that and never got, beaten since. So yes, we can assume that this is some sort of biological limit as long as we don't improve it. But that's an important if, So yeah, I still believe that, of course, if you fix problems where they are all over the place, you should be able to live. I mean, I don't see why there would be a biological limit.
First, I want to ask, can you rejuvenate neurons? I mean, they're accumulating damage all the time.
Yeah, but
sometimes they become like less functional. I don't know, you become senile or some of the neural paths disrupted or whatever. So it all affects our brain.
Sure. So something that is also a common misconception, the neurons don't divide once they are differentiated. but you have
Mm-hmm.
stem cells neurons.
Yeah.
And this one looked like little sphere, I mean, they actually look more like fibroblasts, but you can basically take stem neurons and reseed, I would say, your brain with those stem neurons. They will replace the old ones. So that would be one possible solution. Then if you take a cell itself, there's to some extent a possibility to rejuvenate that cell. Like if you overactivate autophagy, if you manage to clean up the cells from all the aggregation of problem that it had, of course, if the damage are not too serious, if the damage is too serious, actually in biology, if damage are too bad, you better kill the cells and make a new one. It's cheaper than to try to fix it. These are already two paths in which you can either to some degree rejuvenate existing neurons or create new ones. And this was done. For example, I think there's recently some research on Parkinson. So Parkinson is one of those, disease for which there are no cures whatsoever. No drugs can even slow it down. There's only drugs to reduce the symptoms, but there's nothing to cure it for now. But there were some research on stem cell, so dopaminergic neurons, the one responsible for Parkinson, which were injected, and that allowed for reversal of the disease to some degree. So it is possible.
I would love to go a little bit back to aging as a concept. There is a popular narrative in the longevity community that says that aging should be named a disease. Why aging is still not a disease?
Yeah, I heard that a lot, yes.
While we already found out in this discussion that aging is a very, very complex set of conditions, and you cannot reduce it to one thing, do you believe that naming aging a disease would solve something?
Well, I mean, the people who are asking for it, they're asking for it for a good reason. It's because once you declare it a disease, then you can, basically have fundings for that will be more focused. You will have clinical trials that will be more defined. So that's the reason. It's a technical reason, basically. It has no other. Purpose than, of course, it's just name, right? Naming something a disease is just one way to do it. So it would increase the medical and the biotechnological aspect of aging and longevity research, right? The part that would probably suffer from it a little bit if you were to switch from what its current situation is to calling it a disease is the rest. So, for example, supplement industry relies on the fact that it's not a disease. Because the moment you say it's a disease, you cannot have a pill that say it acts on aging because then it's a drug. So you cannot. And even the cosmetic industry is also in that situation. Anti-age, you will see that everywhere on every cream in the world would be a forbidden term because it would be the same thing as saying anti-cancer. And there is very strict regulation that as long as it concerns a disease, only the pharma industry is allowed to develop solutions because they are under much more strict rules than the supplement and the cosmetic industry.
Oh, this is a very, very interesting perspective. I've never thought about it, but this is really, really smart. So technically, pharma should be voting for aging to be
It's in their interest.
declared
It's in
as
their
a
best
disease.
interest.
This is really, really smart. So I wonder, currently there are so many anti-age measures from conservative to quite extreme that you can use to slow your aging. Some people even want to reverse it. So
Me?
we have What are you doing actually to reverse it?
I mean, I have my own, I have my own skin therapy. I also have my own supplement. And these are the things that, that I do. I don't do so much, I have to say. I did improve my sleep a lot because I know that for me it was a problem, something that I cared about. But I still don't do sport, for example. So I'm not very extreme, and I don't take 100 different kind of supplement and I'm still hoping, I believe in technology. I'm a scientist, right? So I believe that technology that we will develop will be the solution. So I'd rather go for some things that are more advanced rather than trying 100 different things that probably have very little impact.
It looks like a spirit of Brian Johnson is among us currently. I agree that he's a great showman, definitely, and he brings a lot of awareness to longevity space, although sometimes it's a bit cringy what he does.
I agree.
What do you think of what he's doing? I don't know, longevity protocol and rejuvenating his penis or whatever happens
Yeah.
there.
So, I mean, basically, if you ask me this question as a scientist, I will tell you basically this is not science. Well, he's not a scientist and he's not a medical doctor. That everybody knows, right? He's a businessman originally, and his approach is not very useful scientifically. It's something that he does for himself, and it's also like a whole marketing show and something that we understand there's a business behind it, or there will be. And
Blueprint.
for sure. And so that can easily be understood. So, but it has no scientific value because this N of one that a lot of people are talking about. So experiment on one person has no scientific value, basically, especially if you're doing 100 things at the same time. Like, how do you know what does what? It's not possible. And on one person, one person is so complex that you can't really expect to draw any useful information out of that. So the scientific community of aging and longevity, they all agree on saying that this is not the way. On the other side, there's this, let's say, biohacker community. So I'm a little bit of biohacker, but not really because I'm not doing much, but I'm still doing a few things. But as a biohacker, yes, it's interesting, but not just him. You have to take all of them together, what is being tried. So the fact that trying to test things that are a little bit at the limit, that's intellectually interesting. It has to be more than one person, has to be, done by several people, but those are like preliminary results. That's what we call, as scientists, when you do an experiment, you first do it small scale, you kind of get an idea of where this is going, and then you do your proper experiment with more replicates and more everything, right? So, but these are all preliminary results, basically. What you can get from what he does or what from the biohacking community does, those are preliminary results that can give us hint of where we should go among the things that already exist, because of course they are not inventing anything. They're just taking the things that are already available.
I want to argue here a little bit from
Please.
many talks with scientists and biologists and people who run citizen science projects. So here I would mention probably Ethan Perlstein with his N of one rare disease project. I would say, I don't know if you know him. He has a project called Perlara, where he develops drugs using yeast avatars for kids who have rare genetic disease, like monogenic diseases. And he has several success stories when the N of one study resulted in having a group of kids. So they started with one girl who got good results, and then they expanded in like 40 people, and probably now they're already licensing, if everything is all right, this specific drug to be used in case of this disease. So this is one thing that started like an N of one, which is of a limited scientific value, but can be translated into something bigger.
So there are some cases where it can be useful as preliminary results. So it's like medicine, they call that case study, when you have like one case that is interesting, but they just have that one and they study it and they try to get as much information as possible from that single case. Your example though was for genetic disease. So it's a little bit different because it's like really usually a single mutation, a single problem that creates the whole array of symptoms. So it's much simpler, I would say, than aging. But that's an interesting case. But as you described it, basically, maybe from an anecdotal, someone who noticed something, then they upgrade to, let's say, a few dozens or 100 people, and then they try to build it into a proper clinical trial. So this is the proper scientific method, actually. This is how things should be done. It's step by step.
Well, in case when you don't have any like medicine or drug to fix it, of course, you're very eager to try everything.
True,
And hope
but
that
sometimes
it
it's more
works.
dangerous than the problem itself.
Yeah, absolutely. I mean, in case of Brian Johnson, I'm always wondering if you can be...
I'm worried for his kidney, personally. If he really takes 100 supplements every day.
Yeah, I mean, like, is he making a good example for people who are, eager to try biohacking for themselves, so don't want to age. From the other side, he may involve many adepts of his blueprint or his protocol, then make a proper study, and then maybe publish some nice papers in Nature.
Mm-hmm. But I mean, it's true also that the they have now this Netflix thing about not only him, but in big part about him. And at least there's this raising of awareness. So more and more people start to care about aging and longevity, and start to let's say understand the idea that there's possibility to do something about it. If anything, that's a positive, because the more people are invested in it, the more people then the more potential funding there will be, and the more discovery will be made, right? So that's in that sense, yes, that's positive, I guess.
Well, I would say that probably all this idea of claiming that aging is a disease is to give people some awareness that you can do something about it. Because for centuries and thousands of years, people always believed that this is just how things work. Yeah, I mean, like, you can do nothing about it. But then I would ask you, first, what do you think about radical longevity?
Well, you know that you got the answer from the beginning, right? So you know exactly where I stand there. My goal is to live thousands of years. That would be my personal goal would be to live thousands of years, right? So I don't like the idea of, well, the limited lifespan is one problem, but the fact of, getting old, getting sick, that's just something that I'm not particularly excited about, I would say. And yeah, I would rather really put a lot of energy in trying to solve that rather than just accept that this is how it is, right? So of course, in my case, I believe that there's a possibility there, and we are getting closer and closer to a bunch of solutions, maybe not a single one, but a bunch of solutions, yes, that can help us to live healthier and longer. So yeah, that's my view on the topic.
If that would happen, would it be some small steps that would extend the lifespan, health span for extra 10 years, 20 years, 30 years? Or there would be someone had an eureka and found a specific gene that turns off all the DNA methylation and causes chaos in our systems that just needs to be, turned on and off, and then everything is golden.
Yeah. It's a very good question. And I would say probably it would work the same way as evolution does. So people think evolution is something that goes up gradually, but it's not at all like that. It's a stepwise process, right? So you do have like flat moment where nothing happens, and then suddenly big jump where you have big change happening. That's how evolution functions. And that's probably how the discovery so it won't be all at once, but there will be like some big steps. And we've seen some already. Like, for example, this idea of the implication of DNA methylation in aging. That's something that 10 years ago, 15 years ago, people would completely ignore. Would be more focused on mitochondria, for example. So mitochondria produce energy and ROS. It makes more sense, I would say, to think that this is more of a clock. And it still is, it's still an important part, but DNA methylation was completely ignored. So that constitutes a big step at the scientific level. But then, of course, to come from this discovery to cures, that take also some time, right? But these are still big steps towards solutions, I would say. So this is something. But I would also think that it might happen the same way as it happened for AI. In AI, we've been talking about AI since, 50 years probably. And you can see how stepwise it was. I remember when I was young and suddenly there was this AI that could beat the champion of chess. You probably remember that as well, right?
Yeah.
Kasparov, I guess.
Yeah.
And this was really amazing. And we were like, okay, that's it. Here we are. The AI is here. And it wasn't. It was one big step from where it was, but it was not there yet. And then the other things happened. Like a huge one was this program developed by the team of Google to see the protein folding.
AlphaFold.
You heard about that? Yeah, exactly. AlphaFold, who has a Nobel Prize for it. So this is also a big discovery in AI. And then you have, of course, ChatGPT and the likes that are completely different from AlphaFold, different technology, but also represent a big step forward and getting us closer to AGI in that case. I think for aging, it's something similar that we have to expect. We've seen already progress over the past 30 years. We see an acceleration of discovery. We see that more and more things are being discovered, more and more scientists are being involved, more and more discoveries are being made. And, there will be progress that will probably, but there might also be some period where it will stagnate a little bit, where we can manage to increase health span for 20 years, but that's it. And we don't manage to go much further than that. So the point where we can really, let's say, solve aging completely, so reverse it even, so take a series of whatever pills or treatment that allow us to be biologically 20 years old, which is as pretty much as young as you can be. That would be, then we say case closed. That's it. You can live forever if you can be biologically 20 years, not forever, but you know what I mean, right? So you're not, aging is no longer a problem if you can either remain or return to your biological 20 years old.
Which technologies do you think will be contributing the most to solving this problem? I mean, AI? Protein folding, whatever else?
I mean,
engineering?
AI. Hopefully, AI is a tool. AI is not really in the mix of the things, because AI only can, at least now, AI can only use what we know. So we are still limited. Biology is still to some degree a young science. It's not really that young, but it's and it's extremely complex. It's more complex, I would say, than any other science. People would think that physics is more complex, but that's not true. Biology is much more complex and there's a lot of unknown still in biology, right? And we're dealing with a lot of things that are interacting with each other. And so AI might help us with that, let's say, to handle the level of complexity that we're getting drawn into, but also AI, for the moment at least, cannot make big discovery. Only experiment can make big discovery, and AI cannot do experiment for now. So, it's limited to our current knowledge. It can analyze data. So it's useful, for example, for drug discovery, because it can pre-screen, molecule, but still the molecule have to be tested at the end. So that doesn't change anything. It just help a little bit the first step. So before we have massive screening of molecule banks of molecules, of millions of molecules, these still exist, of course. And AI is one way to shorten that step, but that step is one among many. The other step are actually the hardest and the longest to deal with, testing the drugs on different models, showing that it works the way it works, seeing all the side effects, doing all the clinical trials. That's what takes time and money, and AI cannot replace that for now, right? So we're still,
AI is off the table. What else will save us?
We are dependent on discoveries of scientists, right? So this is the situation. So we have right now new options like this DNA methylation, for example. We also have a little older solutions, but I haven't been fully investigated. For example, the cell replacement that I'm personally quite interested in. We still have a lot of things that can be tried in those areas, and they make sense. They make sense that if you replace broken system by new ones, then you should have beneficial effect. So yeah, I would say these two are probably among the big ones. Maybe genetic modifications through gene therapy. Once we really understand well what is the impact of adding a gene and controlling its expression, that could also potentially be very interesting, especially if we start adding genes that are not ours. So we borrow from the rest of the animal kingdom, or even plant or bacteria, some solutions that they found, and we use them for our advantage. That could be interesting as well. But now we're talking science fiction, right? But
no, actually, I think
but it's
not.
technically possible.
Well, at least I know some people from the radical part of biohacking community who definitely would be happy to inject themselves with some alien genes of star or whatever, just to try it out.
Yeah. But that's a risky bet, because you don't know what it's going to
Yes.
do. Yeah. So that's the problem. But it's interesting. And there are things that, once we understand, like, for example, there was this naked mole rat. Naked mole rat, this ugly yet very interesting animal.
And the very, very, I would say it's a mascot of longevity.
Yes, absolutely. And they try to dig into its DNA and its physiology. What's so special about it? Why it doesn't seem to age? Why it can reproduce so long into its adult life? And so they found some stuff, like weirdly enough, hyaluronic acid was interesting in those animals. Hyaluronic acid is the stuff that they have in their skin that we have as well, but theirs is more complex than ours. So we're like, okay, if we use their hyaluronic acid in our skin, maybe our skin at least can remain young. When you look at their skin, it's not obvious, right? But actually, they have very good skin in their own way.
You see, this is the skin of a mole rat.
Yeah, exactly. That's not very
It's
seducing,
impeccable. This is spectacular. You mentioned DNA methylation several times today. There are now many startups that are selling this DNA age tests based on DNA methylation.
Right.
So what I've heard, we know that we are not aging evenly. Second, that actually the result of this test can change in a significant way, depending on the lifestyle. If you change lifestyle, so the result of this DNA age can change. So what kind of valuable or useless information a person can get from this test?
Yeah. So that's actually, weirdly enough, it's completely unrelated to the other part of DNA methylation that I mentioned.
Okay.
So yeah, I know it's strange because it has the same name and it talks about the same thing. But in the case of, we're actually talking about aging biomarkers now. And so these are those aging biomarkers. There's plenty, actually. There's a lot of things that you can look at that we know change with age and that are characteristic to a certain biological age. So these are like DNA methylation got famous actually also because of that, let's say, level of precision that it offers at the population level, at least. So if you're taking an entire population and you're checking for that DNA methylation, and you can supposedly get very good information on how old they are biologically versus chronologically, right? There is no perfect aging biomarkers. So there's not a single one that will be enough to really tell you where you stand. It gives you an overall information and it can fluctuate from markers to markers. So the more type of markers that you look at, that's actually the more you have a better picture of this diversity of aging that concerns you. But of course, most of them are based on blood. So they give you markers. So you can expect that many things end up in the blood. So you can have a good overall picture. But if you're interested in your skin aging, probably this blood biomarker is not going to give you much. So it's not going to be enough, at least. And then for blood, for skin, you will have other completely different biomarkers. The test of elasticity, the different light to check different wrinkles and stuff. So there are other ways to measure biological age of the skin. But then you could ask the same thing about the eyes. You can ask the same thing about the heart, brain, and everything, right? So these different biomarkers should somehow correspond to these general markers that give you an idea of your overall state. How precise they are, it's still under debate, to be honest. It's not 100% guaranteed because when you try to, I don't know if you tried them, but if you try one, you decide that, okay, this one seems interesting. Instead of buying one, you buy three. And on the same day, you will test 3 times the same thing. And would you get the same result? Or if you take one day and then another one the next and another one the next, theoretically, your biological age shouldn't change in 3 days, right? Well, it will, and that's the problem. So there are fluctuation depending on which biomarker you're looking at, but there are some that do fluctuate more than others. Right, so you can measure, for example, glycans. That's something that is pretty popular as well, glycan age. But this one is particularly sensitive to inflammation. And inflammation, we know, can fluctuate a lot. Like, for example, I was sick last week. If I take my glycan age last week, I would be probably 10 years older than I am now because my inflammation was through the roof because I had right. So they are, it doesn't matter because inflammation is an interesting marker also for aging. You just have to be aware of what you're looking at and you have to put it in the context that give you this specific information. Once you understand the thing that you're measuring, then you get a better idea. But there's not yet an absolute biomarker of aging. Probably there never be a single one. So more and more companies, they try to combine them. They offer you like an overview of markers and they calculate their own thing. So that's, yeah.
Practically, I mean, like they're using the same matrix. This is still DNA methylation. Yeah. So genes that are like on and off. So methylated or non-methylated. But the tests are just taking, like we have how many? 20,000 genes in total in DNA.
Genes,
So,
yes. DNA
yeah.
methylation, much more.
Yeah. So why much more? What
Because
else
it's
can
not
you methylate there?
one for one. It's not one for one, and it's not
So
that
it's a
simple.
pattern.
Yeah, but
It's a pattern.
Yeah, but it doesn't work like that. So when you look at DNA methylation tests, they were not based on genes that have an impact on aging. It's completely unrelated.
How does it work?
It works by, actually, it's mostly AI. So they are gathering a lot of data on DNA methylation profile. You basically look at the DNA and on which specific spot you get presence of methyl. Right? This little CH3, right? So you look at that over a big population, and you take as an output the chronological age, for example. And then you will see that the population at different age have different specific markers in different specific position. But nobody cares what those markers do. I mean, it's interesting scientifically, but sometimes we have no idea. That's what I was saying earlier. Biology has the problem of being limited in knowledge. Some are placed in places we don't even know why would they have any impact. No idea. We just know that statistically they are more present in people around 60 years old rather than 20. So we know, and that's it. That's all we need to know, because it's a marker. You don't have to have an interpretation behind it. You just have to know it's precise.
Okay, so and it's a set. So like several spots somewhere in DNA and a pattern that is identified through a huge data set. And then you can take my biomaterial and say, okay, Maria, in the spot 1, you look like you are 62, but in the spot 2, you look like you are 24. Well, somewhere.
Normally it shouldn't fluctuate that much. No. That's the point. If it fluctuates that much, then the test is really bad. But it could be that one will say you're 37 and one will say you're 42. That's possible. Because that's within the margin of error, and that's within so that's the point. Each test will be more or less precise, and there are fluctuations. So the point is, because they are measuring this, so they get from your blood, I think. I'm guessing it's from the blood, right? You got a bunch of cells. In those cells, you have DNA. So it's an average, of course. It's an average of the methylation profile of the cells of that blood sample. So if you were to take that blood samples in another organ, or from different cells, then you will have a different profile for sure, because then it's different cell type even. So each cell type has completely different DNA methylation profile, because DNA methylation, the main function is what you were saying, is regulation of gene expression. So, they have a purpose, right? They're not just there for us to guess age, right? So the main purpose of DNA methylation is the control of gene expression. So in a skin cell, you don't need all the genes that are used in a liver cell, right? So all the liver-related enzyme will be switched off in a skin cell. So they will be methylated. They will have something to block them from for this gene to be expressed. That's a simplification. There's more things to regulate transcription. That's one of them. And so, that only works, of course, in one cell type. And so, you have, but even within that cell type, you can have some level of fluctuation from one day to the next. Well, normally not so much, but you can have some. And so they use this calculation based on tons of data to evaluate your biological age. Basically, it just means your blood at that time look more like the blood of someone who is 35 or more like the blood of someone who is 45. That's basically what it means. That's nothing else.
What's the point?
What's the point?
To do that out of only curiosity, or there is
no. That's a very good question. What's the point? What's the point is, if you do it as for personal purpose, right? So you made this test and you see that I don't know what's your actual age, right? So I'm guessing somewhere between 35 and 45. So let's
37. You were right.
So clearly closer to 35. But let's say that your test say 45. Then you will be a little bit stressed, first of all, but it will tell you, okay, maybe in your lifestyle or in your diet or in your, there's something that you're doing that is wrong, or that you're not lucky and you got genes that unfortunately make you age faster, or you had disease that make you weaker and that made you overall aging faster. right? So this is an information. What you do with that information is either you try to change your lifestyle. So if you are a heavy smoker and then you see that your biological age is 45 instead of 37, then you know, okay, like, that's pretty obvious what you have to do, right? It's not always that obvious, but sometimes it is. And so that's one aspect of, let's say, biomarker for people. But the main interest for scientists is that this can allow you to do tests on molecules and see their effect without having to do the whole lifespan experiment. Because if you want to test, let's say, on mice, mice live up to 3 years, between 2 and 3 years. And so your experiment lasts that long. If you want to have a population of 100 mice and test the molecule, then it will take time. But if you have precise biomarker of aging, then you can make it just during 3 months. And they were supposed during that time to age of 3 months, because for 3 months for mice is still measurable. It's like few years for us. And then you can shorten your experiment a lot and you can test more molecules. So that is the, let's say, the scientific benefit of having precise aging biomarkers.
So actually it's a way to optimize the research.
It's
practically.
crucial. It's crucial to accelerate. And I think the people who were involved in the discovery of biomarker of aging, that was their first purpose. It was not for every people to guess their age, their biological age. Their main purpose is to accelerate the aging discovery with proper markers, right? I mean, it works for biomarkers of cancer as well. You prefer to have early detection of cancer, know exactly that this exists, or rather than wait that you have giant tumors and then you can say, oh yeah, that's cancer. So yeah, for aging we have other markers.
Yeah, I mean, like, I'm so much on the side of prevention. Yeah, and not on the side of how the current medical system functions. Yeah, and if you are able to predict illness or aging or whatever very early, it's much easier to fix it compared to some organ becoming fully non-functional because of tumor or whatever else. Yeah. Yeah, and this is actually interesting why all our medical system is like that. It seems that it would be, probably we didn't have enough knowledge to predict it that well earlier. That's why we were only working with let's cut it out.
Yeah, no, true. No, so biomarkers are always very useful in science, and they that's why we're working hard to try and find new ones and more precise ones, so that would really definitely boost the research. And of course, the point is, like you're saying, to have a preventive measure rather than corrective.
So to wrap it up, I would want to ask you like a small prediction. Let's imagine it's the end of the century.
Okay.
And what can we really expect in terms of extending lifespan and health span?
The end of 21st century?
Yes.
Well, the end of 21st century, I very much hope that this will be solved, because or else I'm screwed, right? So this is definitely has to be solved within the next 20 years, because there's also another aspect that we didn't talk too much. I mentioned it for cells, but that's also true for humans. Even if we find a cure for aging, let's say that we do, there's still chance that, I mean, there's still the risk that there's a point of no return. Like you couldn't apply to someone who is 95 and already close to death, because the level of damage is too high, right? So all those therapies that are being developed, they would work, of course. Exactly what you said, preventively is always better. So if you were to give anti-aging medicine to someone who is 25 and make sure that their aging just kind of stop and they stay at 25, that technically should be easier to do than to have someone who is 65 and trying to make him 25. There's a lot of things to be fixed, right? So a lot of things that has been damaged during these 40 years.
I have a brilliant example for that. So one fellow lady running a biotech startup for rejuvenation and gene therapy wanted to get herself test subjects. So she wanted people who are, aging to participate in the study.
That's easy to find.
But the problem was that people who are like 50, 60 years old, they already have a lot of other diseases that would disrupt the results of the study.
Yeah.
So practically, she said, well, I want this like 60 years old who started to care about their health when they were like 25 and continued to do that till 60. And obviously it's very, very hard to find. So it looks like there is a problem here. So you can only like start your whatever gene therapy or anti-age treatment if you are very responsible when you are maybe 30, and it's the last resort. But if you're already 60, like you're like, okay, I will go and die somewhere.
Well, not necessarily. You know, I actually have the opposite problem because like we were saying at the beginning, part of my research is on skin, right? And the skin treatment that I developed, the results are more visible on 60 years old people versus 30 for the very simple reason, because there's more thing to see. Like a 30 years old is almost like 20. There's not much difference, right? Because aging is exponential. So the aging at the beginning is very slow. And someone who is 60 have very clear aging marking on his skin. So if something actually reverse it, it would be more visible on someone who is 60 than on someone that is 30. So, you know, they will only, 30 years old will only see small improvement. So that's, let's say, the paradox, but that depends on how efficient the treatment, of course. And it's not true for everything. Like some things can be reversed to a certain point. Like if you are like stem cell exhaustion. So for example, if you're losing all the cells in your hearing and become deaf, then unless you get implant of new of those cells, then you cannot just magically come back, right? So, or if you're losing your hair, like, you know, unless you implant new ones or find a way to trigger the growth, that's personal problem. Or the hair turning white. It's the same story. It's one cell that is gone. So, you know, unless you bring a new cells, there's no way that to reverse it.
There is some stuff that cannot be reversed. If it's that, it's that. Well, I mean, only if you
we don't know.
there.
We don't know if there's a limit to that. But yeah, it's something that is worth thinking about.
Oh, I love it. Thank you so much. I loved this discussion a lot. I've learned a lot of new stuff about DNA methylation and the complexity of aging. So, last words.
It was a real pleasure for me as well. I enjoy this kind of discussion.
Thank you so much.
My pleasure.
See
Bye.
you.